let's see if having a dog makes people happy. Okay, let's say that's our research question now. So we're trying to see if there is a relationship between having a dog and not having a dog. This variable, I put the variable dog, which does not have or has, but it also has some categories there that are, no answer or they were not asked the question. So I'm going to filter those out. So for the variable dog, I'm going to filter this IAP or no answer. And now we have it. So does this seem to be a relationship here between having a dog and not having a dog and happiness? How would we go about this? Well, this is the frequency distribution here on the last column. This is the frequency distribution of the variable happy for all respondents, right? For respondents that answered this question. And this is the frequency distribution of happiness for respondents that have a dog. And this is the frequency distribution for respondents that do not have a dog. If we compare these two, we see that there is a difference, right? It's about 9 percentage points. And, it seems that respondents that have a dog are more likely to be very happy than respondents who do not have a dog. Okay, do we agree up to that point? Yes or no? Yes, okay, good. So let's now, this is the result in the sample. So we're going to do a hypothesis test. We're going to see if we have this relationship also in the population, right? So let me go back to the values now. And I just want the numbers. Okay, so we're going to start with this table here. All right, so the first thing we do in a hypothesis test, right, is state the null hypothesis. And the null hypothesis is what? That there is no relationship between having a dog and happiness in the population, right? And the alternative hypothesis, right, would be that there is a relationship between having a dog and happiness in the population. All right, good. We are way on our way now. Now, so what would be the next step here in a hypothesis test? Anybody? You can go to your lab and see.
Degrees of freedom.
Okay, and in the degrees of freedom, what is it that we are trying to find out of that? We want to know, okay, we want to determine the degrees of freedom, right? And we do that because we want to calculate that critical value, right? We want to know how samples from a population where the null is true are related. Oh, I mean, are distributed. How these samples are distributed. How the chi-square statistic for these samples is distributed. So, so we're going to determine the degrees of freedom to find the critical value. Okay, so the degrees of freedom in a chi-square test is determined by why? By what formula? Is rows minus 1, right, times columns minus 1, right? That is going to give us our degrees of freedom. In this case, how many columns do we have? And we don't count the totals, right? So we have two columns and 3 rows. So this would be 2 minus 1 times 2 minus 1. So, sorry, 3 minus 1 times 2 minus 1, right? So equals to, there's 3 rows and 2 columns, and this equals to what? 2, right? Okay, so there's 2 degrees of freedom. So we know that when the null is true, and when sampling from that population where there's no relationship, the chi-square statistics that we get from those samples, they would follow a chi-square distribution with 2 degrees of freedom, right? That's why we do this. They would follow a chi-square distribution with 2 degrees of freedom. Now, we are we're going to do this critical value, and the critical value, what is the critical value? The critical value is the it's the value of the chi-square distribution, right, that we would get less than some alpha % of the time. Right, we're finding that, so if we have this distribution where null is true, we're looking for this value of chi-square that it would be very rare, right? And this alpha is the probability that we would make a mistake. We usually, in social science, alpha is 5%, right? So we're looking, the critical value is the value of the chi-square distribution that we would get less than 5% of the time. Okay. So to find the critical value for an alpha of 5% and 2 degrees of freedom, we can use the table, right? Or we can use the chi-inverse function. So we can use, we can have equal to chi-inverse, and this is a little formula that we have in Google Sheets or Excel that tells us the value of the chi-square distribution for a given probability and for a given distribution, right? In this case, the distribution is 2 degrees of freedom and alpha is 0.05. So for 0.05 and 2 degrees of freedom, the value is 5.99. What does this mean? This is the value of the chi-square distribution that we would get less than 5% of the time in this case, right? So this means that when we have a chi-square distribution with 2 degrees of freedom, we would get values of 599 or higher 5% of the time, right? That's our critical value. Good. Now, the next step is we need to calculate our the test statistic for our test, right? um, our table. That is the next step, right? This is all about the null. When the null is true, when we're sampling from a distribution where the null is true, this is what happens with the chi-square statistics. Now, how big is ours? How rare is ours, right, compared to this? Now, to do that, we have to get three tables, right? The observed, right, frequencies, which is just this one, right? So I'm just going to copy that one. Oops. I'm just going to paste the values there, right? This is the same table. I just copied it. These are the observed values. Right, I'm just going to put a line there so that I don't get confused with the totals. Okay. Good. Now we have the observed values. I'm just going to paint them. What else do we need? We need to compare those observed values to the expected. The expected, absolutely right. And these expected, we're going to paint them some other color. Now, for expected, I'm just going to copy this and then I don't know why I always try to do that. Okay, so the expected is what the table would look like if there was no relationship, right? So, all right, the expected comes from a little formula, right? That it is for each cell, we have to find the expected value, and it comes from the total in the row times the total in the column divided by the grand total, right? So for this cell, right, it would be given by the total in the row, which is 108, times the total in the column, which is 168, divided by the grand total. That's 27. Okay. Now for this row, it will be the total in the row times the total in the column divided by the overall total. For this one, it would be that total in the row times the total in the column divided by the grand total. Now, this is the only thing that we can not ask Excel to do. All right, now here's a trick. Now, if you wanna, if you wanna check your work here, if you did this correctly, the expected ones, when you add all the numbers in there, that should add to the total, right? And you can check here, the sum of all of them is 671, and that's the same as the grand total. If you add the row, it should be the same as this, 108. If you add the column, it should be the same as the column total, 168, right? So if you did this correctly, the row should add to the total in the row, the columns should add to the total in the column, and all of them should add to the grand total. Okay, Now, this is what the table would look like if there was no relationship at all. Now, if you compare that to what we have, you know, there is some differences, right? So anyway, I think we're going to have a big chi-square statistic here. Now, the third table that we have to do is the one of chi-square values, right? Equal to chi-square values. Oh, I'm not going to put the equal there. So chi-square values, this is the table. And for this table, the formula is a little bit, you know, more involved, but not that involved. So this one is the observed for each cell, right, minus the expected. We're going to get that difference, and we're going to square that difference so that it's always positive, and we're going to divide everything by the expected. Okay, so we're going to do that for all of them. Okay, let's just copy that. Okay. And we're going to paint these some other colors so that we don't get confused. Okay, so we do that for all of them. And this one is a little easier. So we're going to get two parentheses there. So we go with the observed for that cell, right? First cell, first column, observed minus the expected, right? Same for that cell and that column. That little hat, right? Shift 6 means to the power of, right? And that's 2 squared. We close the first parenthesis, and then we close the second because we're dividing everything by the expected. Whoops, there was a problem there. Oh, I have one more parenthesis there. Okay. Now, let's check that. Okay, it's the same cell, right? First column, first row. Sometimes some of you, I think, you know, didn't match your cell, your observed didn't match your expected in some of them, and that may have created some problems. Now we do this for all the cells. We can also just copy this because it's, you know, the cells move. You can actually drag them. You cannot do this on the expected, because you don't want them to move. These are, you know, fixed. Anyway, so now we have this, right? For each of them, we use the formula. The observed minus the expected, we squared that difference, and we divided that by the expected. Now, the chi-square statistic, right, for our table is just the sum of all this, right? So the sum equals sum of all these chi-square cells. Huh, it didn't let me. That's strange. Okay, so sum, let's do it there. And so it's all these cells, right? From B24 to C26. And the chi-square is 8. 8.23. Now, what do we do now? What does this mean? What do we compare this with?
Our critical value?
Yes, okay. So our critical value is 599. And the chi-square statistic for our table equals 8.2324. Right, so let's think about this for a minute. We said that our critical value is the value of the when the null is true, right? We would get chi-square statistics of 599 or higher only 5% of the time. Only 5% of the time. Now we got one for in our table. We got a chi-square statistic of 8.23. How likely is it that we would get a chi-square statistic of 8 if we were, you know, if the null was true? If we know that it's only 5, we're going to get 599 or higher 5% of the time, we would get 8.23 or higher much less than 5% of the time, right? That would be very rare to get an 8.23. It's very rare to get this, right? Because we get this or higher 5% of the time. This is even more rare. Okay, so when comparing, right, our chi-stat is bigger than the critical value, right? So when that happens, when our chi-square statistic is bigger than the critical value, we can what? Can we reject or not reject?
Not.
Our chi-square statistic is bigger than the critical value. So we can reject. We can reject the null, and I will explain why in a minute. Okay. There's one more thing we can do, and this is the p-value, and I think this would probably clarify things a little bit. Okay, so to get the p-value, we can use this chi-test function. Chi-test. And the chi-test function asks us, we just need two tables, right? We need the observed, right? And we need the expected. That's all we need. We select both and we click enter. And we get this probability. Now, the p-value is, and this is how you will, and this is how you would interpret a p-value, right? For going back to the question before we started this. So the p-value is the probability that we would get a chi-square statistic as high as the one we got if the null was true. Okay, that's like the generic definition. So what about for this particular p-value, right? It is the probability that we would get a chi-square statistic as high as the one we got. What's the chi-square statistic that we got? It's 8.23. So the p-value in this case is the probability that we will get a chi-square statistic as high as 8.2324 if the null was true. What is that p-value? Is 1.6%, right? There is a 1.6% chance, right? That's the probability that we would get a chi-square statistic as high as 8.2324 if the null was true. Okay, that's what the p-value is. The p-value is the probability that you would get a test statistic as high as the one you did if the null was true. Now, in this case, if the null was true, we would get a chi-square statistic as high as the one we did less than 2% of the time. Less than 2% of the time. If we were really sampling from a population where there is no relationship, we would get chi-squares of 8.23 or higher, less than 2% of the time. Is that a small probability to you? That is pretty small. And in social science, like we said, we give ourselves about 5%. 5% is rare enough. In social science or the courts, 5% is rare enough. If there's less than 5% of the time, if we see something that occurs less than 5% of the time, then we see, well, this is not really common. It's not. It's probably, if we would see these statistics less than 2% of the time when the null is true, then our table probably did not come from a population where the null is true. And that's why we can reject the null. Okay, so we can reject the null because there is less than 5% chance that we would get a chi-square statistic as high as the one we did if the null was true. That's why we can reject. And now what happens if we reject the null? What was the null? The null is that there is no relationship between having a dog and happiness level. But we reject the null, so we can say that there is a relationship between having a dog and happiness in the population. And that's all. It's not just in the sample, there is a relationship. Okay?